Big O, without the maths. This is one of the most quoted ideas in software, and one of the most misread. Most people think it measures speed. It does not.
Here is a real week. On Monday, you write a function. It walks the list of orders and picks out the ones you care about. On your laptop, the test file holds 10 orders. It runs in 4.7 microseconds. That is nothing. On Tuesday, it reaches staging. 1,000 orders, 37.8 milliseconds. Still nothing. Nobody comments on the pull request. On Friday, it is in production. 8,000 orders, 2.4 seconds. The page times out. Nobody changed the code. Nobody changed the machine. The only thing that changed is how much data went in. 8 times the orders and 64 times the weight. I measured all 3 of those numbers on this machine. The stopwatch told you the truth every single time. It just never warned you.
So let us name the subject. This is Big O notation, and mostly what it is actually measuring. 3 things this video covers. First, what the notation measures, which is how the cost grows when the input grows. Not time, not speed. Second, the 3 questions that decide which class your code is really in. Third, what it is honestly worth, which is less than people claim in some places and more in others. And 3 things it is not. It is not a measurement of speed. There are no seconds in it anywhere. It is not the maths. There are no proofs in this video, no limits, no algebra. And it is not a way to make today faster. It cannot help you there at all. Where does it bite? Choosing between a list and a set, where the same line of code becomes hundreds of times slower. A review comment that says only, this is order and squared. And a report page that is fine for a year and then is never fine again.
Before any code, one picture, because there is a confusion I want gone early. Most people hear Big O and think it tells them how fast their code is. It does not. It is not a speed at all. Think about a stopwatch. You time one trip. It gives you a real number, and it is not lying to you. But it is a number about one machine, one moment, one input. Run your code on 10 rows and everything looks fine. The stopwatch has no opinion at all about 10 million rows. Now think about a road. 2 roads leave the same gate. For the first 100 meters, they feel exactly the same. One of them is flat the whole way to the horizon. The other one climbs, and it keeps getting steeper, and it never stops getting steeper. Big O is the road, not the stopwatch. It says nothing about your speed. It says everything about the shape of the ground in front of you.
One example for the whole video, so that nothing here stays abstract. We have a list of orders. One order is one dictionary, an ID, a customer ID, and an amount. On a normal Friday, there are about 8,000 of them. This is plain Python on one laptop. No database, no framework, no cleverness. We also have a second list. Every morning, the risk team sends over the customer IDs they want watched, about 2,000 IDs, and the job, all video long, is one question. Which orders belong to a flagged customer? Take order 8,801. Its customer ID is 412. 412 is in the flagged list, so we flag that order. That is the whole task. Every number, every curve, and every piece of code after this is about that one job.
Now go one level below the notation. What is it a measurement of? It measures one thing. How much more work you have to do when there is more data. That is all of it. It keeps the shape of that answer, and it throws everything else away. It throws away the constant in front. It throws away which language you wrote it in. It throws away how fast this particular processor is, the cache, the disk, the network. And it throws away every number a stopwatch could ever give you. Here is the honest part, and I want to say it in the same breath as the did part. That throwing away is the whole point, and it is also the whole limitation. It is why one short sentence can describe your code on any computer in the world. It is also why that same sentence can tell you nothing at all about your Tuesday afternoon.
So let us draw it as roads instead of formulas. There is not one number on either axis here, and that is deliberate. Along the bottom is how much data goes in. Up the side is how much work it costs. 3 ways of doing our job: a nested loop, which is the steep road, a single pass, which is the flat road, and having the problem each step, which barely climbs at all. Now look at the small dashed box at the bottom left. That box is 10 orders. It is also 1,000 orders. It is your entire test suite and every measurement you have ever taken. Here is what the stopwatch says inside that box, measured. One pass, 0.94 microseconds. Sort first, 1.52. The nested loop, 4.68. And now notice something people get wrong. The difference is already there. The nested loop is already 5 times slower at 10 orders. It simply has no consequences yet, because 5 times nothing is still nothing.
Same drawing, same 3 roads. Now keep walking. Here is the sentence to remember. A complexity class is a shape, and shapes only separate at a size you do not have on your laptop. Watch the marker move out. The steep road pulls away, and it never comes back. The flat road climbs steadily, and the shortcut is almost a straight line along the bottom. Here is the same thing in measured numbers. Double the amount of data and time it again. The single pass took about 1.95 times as long. The nested loop took 4.01 times as long, 4 times the work for twice the data. And the halving one took 1.04 times as long, which is basically nothing. Those ratios held at every size I tried, from 500 orders up to 16,000. Double the input, and the flat road doubles, the steep road quadruples, and the shortcut barely notices you did anything at all.
And now, the only counting in this whole video. You can check every line of it yourself. Take the steep road, where every item is compared against every item. 10 orders is 100 steps. 1,000 orders is 1,000,000 steps. 1,000,000 orders is 1,000,000 million steps. That last number is 1 trillion. Now the shortcut, where you throw half away and then half again. 10 items is 4 steps. 1,000 items is 10 steps. 1,000,000 items is 20 steps. Read those 2 columns next to each other. 1,000,000 times more data. On one road, that is 1 trillion times more work. On the other road, it is 5 times more work. That is the entire mathematics of Big O, and there is no algebra in it. One honest note, I counted the real comparisons instead of trusting the formula, and that is how I know the first row is 4 steps and not 3. The usual rounding is off by 1. This video would rather say that out loud than tidy it away.
So how do you know which road you are on? 3 questions decided. Here's the first, and almost nobody asks it. Which operation are you counting? 3 functions here, over the same list with the same n. The first adds up the amounts. It does n additions. The second sorts the orders by ID. It does about n log n comparisons. The third finds the worst offender. It does n hash lookups and then n more comparisons. Same list, same n, completely different promises. Saying order n without saying which operation is like telling somebody the trip is 200. 200 what? Kilometers? Francs? Minutes? The number means nothing until you say what you counted.
Question 2. 3 words that people swap around as if they meant the same thing, and they do not. Worst case is a guarantee. No input can be slower than this. It is the promise that never breaks, and it is what you need when you have a hard deadline. Average case is what ordinary input costs. It is the number people actually quote, and most of the time it is the useful one. Here is why that difference is not academic. I built a dictionary of 5,000 keys and measured a lookup, about 178 nanoseconds. Then I changed one thing. I made every key hash to the same value, so all 5,000 land in one bucket. Same class, same comparison, one function different. The same lookup took 180 microseconds, 1,000 times slower, and it doubles every time the dictionary doubles, because the dictionary has quietly become a list that you have to walk. And amortized is a third thing again. 1,000,000 appends to a list cost 69 nanoseconds each. About 1 in 500 costs 5 times that when the list has to grow. You pay the average, not the spike. That is what amortized means. Question 3. What is n actually? Here is the easy half of that question, and it is the version every course teaches. 2 loops, stacked, one indented inside the other. For every order, we walk every order again. With 8,000 orders, that inner line runs 64 million times. And honestly, this is not the one that hurts you. You can see it. There are 2 levels of indentation right there on the screen. Nobody merges this without somebody noticing. This is the one that gets merged. Count the levels of indentation in this function. There is one loop. For each order, check whether its customer is flagged, and if it is, keep the ID. 4 lines. It reads like the simplest thing in the file. Now look at the line I have underlined. If O, customer ID, in flagged. Nothing about that line looks like a loop. It has no colon. It has no indented body. But flagged is a list, and asking a list whether it contains something means starting at the front and walking along it until you find the thing or until you run out of list. That is a loop, and it is running inside another loop. So it is n orders times m flagged IDs. The second loop is completely real. It is just not written down anywhere, which is exactly why it survives code review.
So I ran it. 20,000 orders, 2,000 flagged IDs, on this machine. With flagged as a list, which is how it normally gets written because that is how the data arrives, 257.9 milliseconds. With flagged as a set and not one other character changed, 0.9 milliseconds, 301 times faster. But the number I really want you to look at is how that gap changes. At 1,000 orders, the set version was 14 times faster. At 5,000, 68 times. At 20,000, 300 times. A gap that grows with n is the fingerprint of a quadratic. 20 times the data made the list version 426 times slower. If it were truly linear, it would have been 20 times slower. It was not. And the fix is not an algorithm. It is a container. One new line at the top. Turn the flagged list into a set. That is the whole change. The loop is the same. The if is the same. The letters on that line are identical. What changed is what sits underneath it. Asking a set whether it contains something is a hash lookup, and it costs the same whether the set holds 10 IDs or 100,000. I measured that too. About 15 nanoseconds either way. Flat. Asking a list costs about 64 nanoseconds at 10 items, 5 microseconds at 1,000 items, and half a millisecond at 100,000. It climbs, and it never stops climbing. Same line of code, different shape. That is what choosing a data structure actually means.
So what is this thing if it is not a measurement? Here is the sentence I would like you to keep. Big O is a prediction about a graph you have not plotted yet. It tells you almost nothing about today. Today, you have a stopwatch, and the stopwatch is better at today than any notation will ever be. But it tells you almost everything about the day your data is 100 times bigger, which is why it is worthless for tuning and decisive for choosing. If you are trying to shave milliseconds off something that already works, close the textbook and open a profiler. If you are picking a data structure that will still be there in 3 years, this is the only tool that can see that far. Now, the cost of all this, honestly, same picture with the thing Big O threw away put back in, the constant. I expected the built-in to win everywhere. Python's sorted function is written in C. The other version is a handwritten single pass in plain Python. Better shape, much worse constant. At 100 orders, the built-in is 12 times faster than the version with the better shape. 12 times. At 1,000 orders, it is only 1.3 times faster. At 1,500 orders, they are dead level. And at 1,000,000 orders, the handwritten pass wins by nearly 2 to 1. So the constant decides who is faster, and the shape decides who is faster in the end. That crossover is a real number. For most code you will ever write, it matters more than the notation does, and it is nowhere in the notation.
2 more reasons to hold this whole thing loosely. The first is that most of the time n is never big enough for any of it to matter, and the cost you are actually paying is somewhere else entirely. I put a real HTTP server on this machine and timed it. 1 round trip to a server on the same machine with nothing on the wire, 1/4 of a millisecond. In that 1/4 of a millisecond, the fast version of our function gets through 3,000 orders, your entire n, several times over, hiding inside one network call that nobody ever looked at. And no complexity class describes that round trip. It is a constant, and Big O deleted every constant on the first slide. The second reason is a limit I would rather state than hide. Big O counts operations. It does not count how far the data sits from the processor, and on real hardware, that gap is about 65 times. 2 functions in the same class can differ by that much on memory layout alone. There is a separate video on exactly that, and this one takes it as read. Take the limit seriously and the notation stays useful. Treat it as a performance model and it will lie to you.
If this comes up in an interview, here are 3 questions and what a good answer sounds like. Is order 1 always faster than order n? No. It is not a claim about speed at all. It says the cost does not grow when n grows. A function that always takes 10 milliseconds is order 1, and at small n, the order n version very often wins. What is the complexity of x in my list? Order n. It walks from the front. A set or a dictionary is order 1 on average. And inside a loop, that is the hidden quadratic we just measured at 301 times. Worst case or average case? Say which one you mean every single time. Quoting an average as if it were a guarantee is the mistake. And amortized is a third thing again, cheap per call when you average over many calls. The strongest answer to any of these starts by refusing the question. It depends on what you are counting and on how big n actually gets. Let me put the whole video back together as one chain. Big O is a shape, not a time. There are no seconds in it. To be a shape, it has to discard things on purpose. The machine, the language, and the number on your stopwatch, which is why small n tells you nothing you can act on. 10 orders was 4 microseconds. 8,000 was 2.4 seconds. Same code. And the worst version of that is never written as a loop. 1 n on a list inside of 4. 257 milliseconds became 0.9. So treat the whole thing as what it really is, a prediction. Useless for tuning today, decisive for choosing tomorrow. And underneath all of it, one habit. Before you argue about a complexity class, go and find out how big n actually is.
Thanks for watching. If that cleared something up, hit like and subscribe so the next one finds you.